Good afternoon, everybody, and congratulations on finishing a pandemic year. It's been a crazy one, and thanks for the invitation to the said symposium. I just wanted to spend part of the afternoon with you telling you about what we're doing in the magnetometer lab. One of the crazy things about the University of Michigan is we're the largest public research university, which essentially means that if you can imagine some human activity, there's somebody here who's studying it. And space is one of the really big things. And you're going to hear later this afternoon from Professor Mike Lamone about the Michigan Space Institute that's going to try to provide some coherence. One of the problems of being at the University of Michigan is there's so much going on. Just being able to navigate and know what's going on is really difficult. And so I'm glad that you've taken time out of your Saturday to learn a little bit of what's going on here at the University of Michigan. Because just like a robot who's exploring a terrain for the first time, we don't know what's over the next side of the hill unless we go. I'm Mark Moldwin. I've been at the University of Michigan now for 11 years, 12 years. I came to Michigan from UCLA, where I was a professor for 10 years, and before that I was a professor at a small engineering college in Florida, Florida Institute of Technology, and I did my postdoc at Los Alamos National Laboratory in New Mexico and my PhD at Boston University, my undergraduate at University of Alaska Fairbanks, but I was born and raised in Michigan. So I came back. I'm a CAS Tech grad from Detroit. In my role here at the University of Michigan, I'm also the director of NASA's Michigan Space Grant Consortium, and I'll have an invitation for you at the end of a description of the work we're doing this summer. I also just want to highlight Laura Ojeda, a colleague professor in mechanical engineering, who's also one of the leads of the magnetometer lab. And so this little collage shows some of our funders for our projects this summer. And essentially what we do is we try to measure and understand how energy from the sun influences the space environments of the planets, especially Earth. And if you think about space, one of the things that's everywhere are plasmas, ionized gases, and those ionized gases, when they move, create electromagnetic fields and magnetic fields. And essentially all of the planets have some type of magnetic environment around it. We differentiate intrinsic magnetic fields that have something going on in the dynamo of the planet or the star that creates the magnetic field, but even in the two bodies that don't have intrinsic magnetic fields in our solar system, Venus and Mars, they still have magnetic fields around them, either due to they used to have magnetic fields and then it had some magnetization in the rocks that's still there, or in the case of Venus, since it has a very dense atmosphere, the upper layers get ionized, so it has an ionosphere, and those drive currents that make an induced magnetosphere. So a lot of magnetic fields. And so one of the things I really like about space physics, and if you think about space science, you can often divide it up into 4 subdisciplines. The 2 big ones are astrophysics, everything outside the solar system, and space physics, everything inside the solar system. And I've always been fascinated with space physics because, as we heard in the previous talk, we get to build robots and go. And so we could ask a question. I wonder if there's life on Mars. Let's go. Oh, like land a Viking and take a picture and there's no bunny rabbits. So maybe it's below the regolith, below the dirt. So we put a Perseverance rover or something like that, right? So we get to go back, or get to discover Galileo saw the moons of Jupiter. Now we get to go there, and as we heard, they could have liquid water life form. So let's go. The other two fields of space science besides astrophysics and space physics are planetary physics or geophysics, and that's interested in more of the rocky bodies of the planets and asteroids and comets. And the newest subfield is called astrobiology, which is a blend of all three of them with biology. So it's trying to figure out the origin and evolution of life in the universe. And so astronomers that are astrobiologists might be looking for extrasolar planets, and space physicists who are astrobiologists might be interested in the upper atmospheres of those planets. And then the planetary geophysicists might be wondering if there's subsurface oceans or whatnot. But as I said, one of the things that differentiates astrophysicists from space physicists, we get to go someplace. So that's what we do. For the last 6 or 7 years, we've partnered with a company in California called PNI. They make a new type of magnetometer that measure magnetic fields. It's called magneto-inductive. It's a very simple design, and we've been putting it through its paces through a number of NASA and DoD grants. This is the chip itself. It's this ASIC, application-specific integrated circuit, has all of the electronics here, and then these three things in red are the three axes, because a magnetic field is a vector, so you have a bx, by, vz, and you can put this all on a chip the size of a quarter. And so we've been doing a lot of environmental testing, shaking it and baking it, and this is a picture of this chip with the ASIC. It's called decapsulated or delidded. Essentially, you can take the plastic out and just expose the circuitry. And earlier this week at Lawrence Berkeley National Lab, it was put into a heavy ion beam line to take a look on its radiation susceptibility. So we've been doing a lot of radiation testing on this chip. And what's really cool, this is one tough chip. Typically for like a radiation belt mission here on Earth, the type of total ionizing dose, or TID, is measured in the tens of kilorads, and a rad is a unit of flux into a mass, joules per kilogram. And humans are susceptible to radiation, and so OSHA requires that if you work in an environment that has radioactive sources, an X-ray machine or Homer Simpson in a power plant, you have to have a dosimeter that measures that fluence. And typically they're measured in fractions of rads, but space is much more radiation. Has much more radiation. But this chip can survive up to about 500 kilorads without any issues. And the other thing that you have to worry about is called single event effects or single event latch-ups, which electronics, essentially, they can have a current spike and cause them to stop working. And we tested this up to 75 MeV. And it still works. So I'm really excited. The results just came out this week. The chip, two of these chips are going to be going on the first piece of hardware for NASA's next lunar mission. NASA Artemis, following in the Greek mythology of the Mercury and Gemini and Apollo type of mission. Artemis, the sister of Apollo, will hopefully have humans on the moon in maybe about 7 years. It's the sort of 2028 timeframe. They're planning to pick the crew soon, and they're hoping to have the next man and first woman, or maybe even an all-female crew, land on the moon as part of our exploration of our nearest body. But the first piece of hardware that's going to be launched is scheduled for January 2023, and that's what's pictured here. It's a power and propulsion element, which is a huge plasma Hall thruster. So if you're into propulsion, a lot of the work done here at the University of Michigan is in plasma propulsion, and a lot of U of M folks have been involved with the company that's been developing this. And then this is the HALO, which is the habitable lab where the astronauts will go. And Hermes, which is another Greek god, was the name of this instrument suite, Heliophysics, Environmental, and Radiation Measurement Experiment Suite. So we're going to be going on to HALO. And to keep the Greek theme, our instrument is called Nemesis, the Noisy Environment Magnetometer in a Small Integrated System. Because this guy kicks out a lot of magnetic field, and we're trying to measure a very small magnetic field of the interplanetary magnetic field. So one of the interesting things, particularly if you're thinking about a PhD, but it could be for anything, what's your reach? What do you want to do? And one of my career goals is I would want to put a magnetometer on every vehicle that is in space. So it doesn't matter if it's a Starlink or the next probe to the outer planets, it should have a magnetometer. One of the problems with space-based magnetometers is it's usually difficult to accommodate them onto a bus. You often need to have a really long magnetic boom that holds the sensor away from the spacecraft, because the spacecraft has reaction wheels or torque rods or radios or batteries and solar panels that create electrical currents that give rise to magnetic signatures. And so another NASA mission that we're involved with called MMS, Magnetospheric Multiscale, is a set of 4 satellites orbiting Earth, and it has an 8-meter boom. And so what we're developing are machine learning algorithms to be able to put these very little, very low power, low weight, low size, low cost, low telemetry systems all over the spacecraft. And so we don't need to be out at the end of the boom. We can measure the spacecraft magnetic fields through those algorithms. So we're trying to revolutionize the way magnetic fields are measured in space, essentially with boomless satellites. And so if you're an engineer, one of the innovations is if you can change something in a good way by an order of magnitude. So if you are an internal combustion engine person and you can improve the fuel efficiency by an order of magnitude, you have 400 miles per gallon, right? It kind of changes things. Or if you're a battery life thing and you only have to charge your phone every 10 days, people will be knocking at your door. So we've been trying to reduce the size, weight, power, cost by an order of magnitude or more. And this little guy, in some cases, are 2 orders of magnitude better in terms of these types of figures of merit. So this little P&I is usually put into a little chassis, and we'd like to screw this to the body of everything that goes out. And a couple of other missions that we're working on right now. One is a MIDEX proposal. NASA selected 6 MIDEX to do concept studies, and they're going to down select in January or so of next year for 2 of them. There's one of them called Solaris, which will orbit the pole over the pole of the sun and be able to look down at the poles of the sun for the first time with some imagers, EUV imagers, and ways to measure the source surface magnetic field of the sun. Have you guys seen the pictures from Juno of the poles of Jupiter? When you look at Jupiter, you think of the brownish, reddish stripes and great red spots, but flying over Jupiter, it looks nothing like it. And there's all different other colors because of different types of chemicals that are making it up to the upper atmosphere. If you haven't seen them, Google Juno, Jupiter. They're just shocking. They're just not what you would expect. And so this is a discovery mission to try to look at what the top polar regions of the sun. And so what we're proposing is to put our little magnetometers on it to be able to measure in situ, or the interplanetary magnetic field, while the spacecraft is imaging the magnetic fields coming out from the sun. So we'll be able to try to connect and fill in these this artist's drawing of field lines. The other big NASA mission is a Living with a Star mission, and the AO, the Announcement of Opportunity, hopefully will be out next week for instruments, and we're proposing to put magnetometers on board this GDC, Geospace Dynamics constellation. It will be 6 to 12 satellites in low Earth orbit that will be sharing different orbital planes, but spread out over local time, and to try to make global measurements of the ionosphere thermosphere system and understand how energy from the sun influences the Earth's space environment. The other thing we're trying to do is change the way we do space geomagnetism. We operate magnetometer systems around the world, and typically a ground-based magnetometer can cost $10,000 to $20,000 and requires power and ability for communication. Things that are in Antarctica, we have to develop solar panels and a whole bunch of batteries and iridium modems, and they have to survive. So we're trying to use this very low-cost system to, again, an order of magnitude, instead of $20,000, $2,000. So we can start spreading these around, even in your backyard. If you don't know, anybody use Weather Underground, the app? Yay! You know, that was invented by students here at the University of Michigan in AOSS, and it was really one of the pushers for citizen science, because Weather Underground allows you, if you have a backyard weather station that you can connect through Wi-Fi to your own house, you can feed your weather data to the National Weather Service. So it's a way of microclimate, because I don't care if it's going to be raining in southeastern Michigan. I want to know if it's going to be raining in my backyard if I'm going to have a picnic, right? So we want to try to get the best data. We'd like to do the same for space weather monitoring, understanding what's going on. So putting GPS receivers and magnetometers in folks' backyard. And we have a group of students this summer helping with a wide range of aspects of this. NASA is also supporting us right now to think about, can this guy work on the surface of Europa? As you heard, Europa is a really cool neighbor, and I saw a number that I haven't verified yet, but it essentially said that there's more water in the oceans of Europa than all of the ocean water on Earth. And you go, that doesn't make sense. Europa's smaller than Earth, but if it has a global ocean of X kilometers of depth, it can have a lot of volume. And one of the cool things about Earth is that wherever we find liquid water, we find life. And so in ice sheets, in hot springs, on the bottom of the ocean, there are ecosystems of life. And so the NASA's astrobiology strategy is to find water. So a lot of the early rovers was to find water. So we now know with Curiosity and Opportunity that the minerals on the surface of Mars only form in the presence of liquid water. So we know there's water. And now we've discovered there's ice below the regolith, and we know there's liquid water. And so the question is, okay, there's liquid water on Mars. Can there be life? And so the next place is, there's oceans of water. on Europa? Are there krill, European krill, European tuna fish, European merpeople? Let's go. And so that's, again, why you're a space physicist. You have a question. I wonder if let's go. Let's put an orbiter. So we have Europa Clipper will be launched this decade, and will be in orbit and fly by Europa, looking for landing spots for a Europa lander by the mid-2030s. And then we're hoping to find plumes and geysers and vents, and so somebody else can design something to melt their way through a ice crevasse down to the ocean, turn into a underwater remotely operated machine, and take some pictures of Aquaman or something. But the problem with Europa is it's orbiting Jupiter, which is 5 times farther from the sun than the Earth, so it's really, really cold, and Jupiter's radiation belts are really, really big, and so they instead of kilorad, you have megarad worth of radiation, and temperatures, liquid nitrogen-y type of temperature. So the experiments that we're doing here are these radiation testing and cryogenic testing to see if our instrument not only can survive, but actually operate. And as I mentioned, we operate ground-based magnetometer systems all over the world, in the Arctic, in the Antarctic, in South America, in Africa, in Asia. And so one of the challenges of any ground-based system that goes from the tropics to the poles is that they have to survive and operate in very different conditions. So a lot of the work is trying to make sure their critters don't chew on cables, or they don't freeze, or humidity doesn't get them. So we work on space technology across the TRL. If you have had a systems engineering class, we often think about the maturity of a technology with a readiness level. So a technology readiness level, or TRL, it's a number from 1 to 9. And 1 is something that we just dream up. It sounds really cool, but it probably doesn't work. And then a 9 means it's been working in space. And so we work across that entire gamut, invent things, and try to develop new ways of doing things. We try to mature things that have been used in other industries. This P&I is an automotive compass. So your car that has a little compass tells you where it is. It might be a P&I compass. And so we're trying to turn that automotive sensor into a space-based sensor. So students work in my lab through a lot of programs, but if you're interested, feel free to email me. You'll hear about the Space Institute later this afternoon. SPERL, the Space Physics Research Lab, is celebrating its 75th anniversary this year. It's kind of hard to believe that it's been around so long, but in 1946, faculty at the University of Michigan that were studying the atmosphere got their hands on captured German V2 rockets and wanted to know, I wonder what the atmosphere is like a few hundred kilometers up. So that was the first launch in 46, and we've been building space instrumentation since. So 2 invitations to you. One, not only is it the 75th anniversary of SPERL, and it's the inauguration of the Space Institute, it's the 50th anniversary of Apollo 15 this summer, and we're going to have a party. We're hoping that it will be hybrid-y, in person with some special guests. But worst case, it will be virtual like this with special guests. But if you don't know about Apollo 15, it's special for Michigan because all 3 astronauts attended the University of Michigan. So this is the all-Michigan crew. And Michigan Space Grant, we're in our 32nd year, so we don't have any nice round numbers like SPERL or the Space Institute or Apollo 15. But one of the things that we've been doing for 32 years is providing funding for student groups and individual students. If you're interested in doing a internship at a NASA center, we help place those. And if you're interested in doing research here at the University of Michigan, we fund you. And if you have a student team or a project, we fund those projects as well. So please check out our webpage. Great. So I'm happy to chat for a minute or two, I see.
Thank you so much for that talk. That was really cool. I I've actually heard a little bit on space weather and everything that goes into it, but like I never knew at least very much about it, and that was really interesting to hear about, and especially with a preliminary data in Europa.
Yeah, if you're interested, there is a 100 level class, Space 103 Introduction to Space Weather. Learn a little bit more about that. And if you're interested in space weather as a undergraduate, there's also a space science minor or major space science and engineering, and there's a lot of upper division space weather classes.
Unfortunately, we are out of time for questions, but if anyone has questions, feel free to put them in the Slack, or are they able to email you with any questions?
Please do, and I'll put it in the chat as well.
Awesome.